Hello and welcome to lecture number 9 in the course Advanced Robotics. In the last class, I had discussed about the inverse kinematics problem, and I had systematically laid out the steps that are involved in trying to solve the inverse kinematics problem of a serial manipulator system. Now, we had also solved some numerical examples in which when we are given the position and orientation of the end effector, how do we find the corresponding joint angles? Today, we'll move on to the next topic, which is Jacobian and singularity. Now, in terms of control, we are going to move the robot, or we're going to move the link of the robot by actuating the motors which are connecting at the joint. And then when we give a voltage to the motor rotates, because of which the joint angle changes, and then the end effector velocity also changes. Now, as far as the user is considered, we are interested in the end effector velocity. That is, I want the robot to go from this point to this point with some velocity, or to go to some point. Maybe there's an object here, and I want to go to this object, catch it, and pick it up and take it to some other point. So as far as the user is considered, what is important to us is to see how the end effector is moving in space to approach a particular point, or to go and catch an object and do some task. Okay, so we are not concerned with what is happening at the joint level. Whereas for the controller, in order to be able to take a manipulator end effector to a particular position, how are we moving there? We are basically actuating the joint motors which are connected to the joints, giving a voltage to the motor is rotating, because of which the joint angle is changing, and then the end effector is going to some point in space. So there has to be some relation between the end effector velocity and the joint velocities, because we are ultimately controlling the joint velocities. Okay. Now the Jacobian relates the end effector velocity with the joint velocities, and we also need to look at the energy consumption. For example, we talked about a manipulator which is performing a task. We said the manipulator should perform the task such that the task is inside the work volume, which is fine. But then where inside the work volume? For example, in the human arm, my work volume is a sphere. It's very large. I can perform a task here, 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 down, up, anywhere. Where will I perform a task? Okay. So to answer that question, we need to look at energy consumption. Okay. And indirectly, we need to look at velocities of the motors. So today we'll talk about Jacobian and then proceed to singularity. Okay, so today we'll be studying about Jacobians, and then we'll talk about singularity. So as I was mentioning that how does a robot actually work? If you look at the actual construction of the robot, we have a joint. Okay, and at the joint, these are links, and at every joint there is a motor which is connected. The motor has an encoder at the back, and there is a gear sitting in front. Okay, all joints have this independent joint control structure such that the joint is actuated by a motor, and there is an encoder at the back. Now, when the motor moves, what happens? The joint angle changes. Theta 1 is here, theta 2, theta 3. And when theta 1, theta 2, theta 3 change, what will happen? This x, y, z and alpha, beta, gamma will change. Okay. So when we are controlling as far as the user is considered, the user basically is interested in the motion of the end effector. For example, if the end effector has to move in a particular trajectory, so the end effector has to move like this. So it goes to this point, this point, this point, this point. Okay, he or she is not really worried about what is happening at the joint level. Another example is when the end effector is picking up an object. For example, there's an object here kept on a table, and the robot has to go and pick it up. So this is the point P2. So the robot has to go there and pick it up. Okay, go here and pick it up in some configuration. So in order to be able to take it from here to here, okay, the actuation or the motors will have to be actuated such that the joint angles change, and the joint angle change will result in the end effector coming from here to here. Okay, so what you're actually controlling the motor, or how you're controlling the motor, is by giving a voltage there. So when you give a voltage here, so let's talk about, in the last class I talked about the actuator space. So this is my actuator space in which I'm going to give voltage, because of which the joint angle will change. Okay, so theta will change, and after the theta changes, and because of the change in angle here, what will happen is the end effector will change, the position of the xyz will change, and this is called the end effector space. Okay, so this is my actuator space, this is the joint angle space, and this is the end effector space, and there can be different kinds of mapping which are going on. Okay, there can be all kinds of mapping, forward and backward. Now, so what we are interested in is, if I want this end effector to move with a particular velocity. So I say x dot, y dot, and z dot. Say for example 1 meter per second in x direction. Okay, this is my velocity in the x direction. Y direct and z are equal to 0, just for example. So to enforce this 1 meter per second motion in the x direction, I have to actually control the motors. That means I need to control the motor velocities, theta dot. So what is the relation between x dot and theta dot? This is what I need to know. Okay, so there is some relationship between x dot and theta dot, right? And that is exactly how I'm going to control my motors. So by controlling the motors, I'm going to get some end effector velocity. And so I need to know a relationship between them. More importantly, suppose there is no relation between them. That means you cannot go to that point. We talked about singularities or solutions not being possible. Okay, so if you end up with a singularity, that's a point where the manipulator cannot go, then what happens to the joint velocities? Okay. The third is, I just mentioned that for a human being, it's a very interesting example for a human being also. So if you consider this to be our arm, and this is my hand, then if you look at our work volume, then our work volume is very large. It's a sphere, right? I had drawn this. This is L1, that's L2. So L1, L2. So my work volume is going to become a sphere of that shape. It's like a sphere, spherical, right? Okay. Now, so this is my L1 plus L2, L1 plus L2. Now, if I want to do a task, if I want to perform a task, okay, where should I perform the task? Where should I do the task? Okay. Now, for example, suppose I'm writing. For example, writing on paper or on a book. Okay. Where should I write? Now, so the first thing is that it should be inside the work volume. So this is obviously understood, is that it should be inside work volume. Okay, but where inside the work volume? The work volume is so large. Suppose I want to write. You can imagine that you're writing with a pen on a piece of paper. So are you going to write here? 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 Where are you going to write? Or if you're eating in a particular way. You're doing a task, you're doing in a particular way. So where should you perform the task? Well, answer of that would be such that it is optimal. This is an answer which a lot of students give whenever they're asked a question that you should do this in a particular way. How should you do it? Well, you should do it in an optimal way. What do you mean by optimal here? Optimal in terms of what? We can say that optimal in terms of energy. Okay. So that would make a reasonable answer, that we are trying to minimize energy. Okay. So it is optimal in terms of energy such that there is minimum energy consumption. And this makes sense, that we should walk in a particular way, we should do a task in a particular way such that the energy requirement for that task is minimum. Because why should we expend more energy? Okay. Now, suppose the energy consumption goes towards infinity, then what happens? Suppose there are points where you cannot go. What does it mean in terms of energy? Okay. So these are questions that we try to answer when we're talking about the Jacobian. Now, in the last class, I had talked about the forward kinematic equations. So let's start off by just looking at this very simple example, that this is my theta 1 and that's my theta 2, and this is my point xy. This is my theta 1. It's on this side. So this is my angle theta 1. That's my angle theta 2. This is the x-axis. That's the y-axis. Okay, so y naught, x naught. That is the point xy. This is L1, this is L2. Okay. Now, what we are seeing is that xy, x and y is a function of theta 1 and theta 2 in this case. Okay. That means there is some relation between xy and theta 1, theta 2. Okay. So we want to find what is this relation, and in terms of velocity, in terms of position. So there is a position relationship, a position relation. So if I take the derivative of that, then I get the velocity relation. Okay. So a position relationship and a velocity relationship can be obtained from this equation. So basically what we are saying is that if you have a function, so this is a function, right? xy is equal to a function of theta 1 and theta 2. So if I write y1 is a function of variables x1, x2, x3 like that up to x, let's say x6, if not x6, let's say xn. Okay, then or let me just say 6. The robot cannot have n. Suppose we have another one, y2 is equal to f2, x1, x2, x3 up to x6. Okay, and y6, so we have this, and we have y6 is equal to another function of x1, x2 like this up to x6. Okay, now I can write this combined as y is equal to a function of x. That is exactly what I've written here. Okay, y is a function of x. Okay, so xy is a function of theta 1, theta 2. You can think about this as being xy, okay, this part, and this to be equal to theta 1, theta 2, theta 3 in that order. Okay, theta 1, theta 2, theta 3 like that. Okay, so now if you wish to calculate the differentials of y as a function of differentials of x, we simply use the chain rule to calculate. Okay, so basically what we are doing the partial I'm taking the partial derivatives. Okay, so if I want to find the differentials of y, okay, I want to find x dot and y dot, that is basically the velocities, right? So what do? And there are how many variables? Theta 1, theta 2, theta 3 up to 6, or x1, x2 up to x6. So what I can do is I can write it this way. Well, let me write it in the next page. So del y1 is equal to partial derivative of f1 by x1 into del x1 plus partial derivative of f1 into x2 into d of x2 plus like this up to d of f1 into x6 into partial of x6. Okay, similarly for the second equation 2 I'm going to find, then I take the x1 into del of x1 plus like this up to the last one, which is del of f2 into x6 d of 6. In this way I continue. Okay, and the last one is going to be my similarly here I'm going to write d of y6 is equal to d of f6 to x1 like this. Okay, I hope you follow. So what I'm doing here is that I want to find the velocity, I want to find the partial derivatives because we have more than one variable. So what I'm doing in the previous case, what is the objective? The objective here is that I have xy here. Okay, I have xy here and I have theta 1, theta 2. Xy is a function of theta 1, theta 2. So if I want the velocities, the x dot and y dot, then I need to take partial derivatives with respect to theta 1, theta 2, theta 3, theta 4 like that. Now I can write this as in short is equal to of f into dx. You can write in short like this. Okay, now we write this as t of y is equal to j into t of x, where j is called the Jacobian. Okay, the 6 by 6 matrix of partial derivatives. Okay, this is called the Jacobian matrix. This is called the Jacobian. What is it giving you? It is giving you the relationship between the differential of the derivative of x and derivative of y here. Okay, now what are we interested in? We are interested in the end effector velocity and the joint velocity, right? So I want x dot and I want y dot, and x and y is a function of theta 1, theta 2, theta 3 like that. So I take partial derivatives with respect to theta 1, then theta 2, then theta 3. In this case only theta 1 and theta 2, such that I get the relation between x dot, y dot and theta 1 dot and theta 2 dot. Okay, so this is my end effector velocity and this is my joint velocity. Okay, so this is the Jacobian that will come in here. Okay, so basically this is just to show what the Jacobian is, how the Jacobian is defined, and what are we trying to do. Okay, so now let's look at our two-link manipulator. let's come back to our two-link manipulator. So this is my two-link manipulator. This is x naught, this is y naught, this is L1, L2, sorry, let me write it this side. So this is theta 1, this is theta 2, this is L1, L2, this is x, y. Okay, so now first of all we need the position relationship. Okay, between x, y and theta 1, theta 2, that's a position relationship. Now forward kinematics is so by using forward kinematics we can get that. Now the procedure is, obviously you have to make your DH parameter table. Number 1 is assign axis, then number 2 is make DH table, then from the DH table make your total transformation matrix from 0 to n, then 4 is find the px, py, pz, that is the distance between all distance between origins. Okay, now we know how to do that. I have found it out in the last class and last two classes I've been doing this. So I'll write it straight here. X is equal to, so what I mean is you get your final matrix T0 to n, and that gives you your px, py, pz here. This will be 0, 0, 0, this will be 1, and this will become cos 1, 2 minus sine 1, 2, 0, 0, 1 is sine 1, 2 cos 1, 2, 0, 0. Okay, now this is the one that is going to give me the position relationship. So or we can just call it, if I say this is x, that is y, and that is z is 0. Okay, so x is equal to for this manipulator L1 cos 1 plus L2 cos 1, 2, and y is equal to L1 sine 1 plus L2 sine 1, 2. Okay, this we have got these two position relationships. So xy is a function of how many variables are there? Theta 1 and theta 2. So just following exactly what I've done here. So if you have, you can imagine this to be a function theta 1, that's to be theta 2. Okay, then theta 3, like that. So first we take the derivative with respect to theta 1, then I take the derivative with respect to theta 2 and proceed. Okay, taking the partial derivative. So first what I do is I take, here there is two thetas, theta 1 and theta 2, right? So what I do is first I take the partial derivative with respect to theta 1. Okay, this contains only theta 1. Then I take it with respect to theta 2. Now this contains theta 1 and theta 2. So what will happen is I get dx. So I get dx is equal to, I take a partial derivative with respect to theta 1 first. So I get minus L1 cos 1, sorry, minus L1 sine 1 minus L2 sine 1, 2. So with respect to theta 1 I've got my derivatives. Then I take with respect to theta 2. So with respect to theta 2 I get minus L2 sine 1, 2. Okay, now the second one is with respect to, so y dy is equal to, first with respect to theta 1, so there is a L1 cos 1, it will become L1 cos 1 plus L2 cos 1, 2. Okay, then I take with respect to theta 2, so theta 2 is here only, so I get plus L2, so this was sine, so it becomes cos 1, 2. If I write in matrix form, then it looks like this. D theta 1 and d theta 2, d theta 1 and d theta 2. Okay, so here I get d of theta 1 and d of theta 2, theta 2. Okay, so what I did is first I took the derivative, partial derivative with respect to theta 1. So I had minus sine here, and then again here, because there is a theta 1 there, so it has become minus sine 1, 2. Then I took with respect to theta 2. With respect to theta 2, this does not have theta 2, this only has theta 2, so it becomes a minus of sine 1 2. Okay, so this is what we call, in short I can write this as, okay, x dot is equal to j into theta dot. Okay, and this j is called the Jacobian. So this is called the Jacobian, okay, the Jacobian matrix. Now this is called my Jacobian matrix. So this 2 by 2 matrix, 2 by 2 matrix is called the Jacobian. What does it relate? It relates the end effective velocity is x dot y dot, okay, which is given here, with respect to the joint velocities, which is d theta 1 and d theta 2. Please note that these are incremental velocities. Okay, this is not an average velocity. So increment d of x, you understand that d of x means a very small change, incremental change only. So this basically means, so this would basically mean this dx, then d theta, these are incremental velocities. Okay, these are incremental velocities. Okay, these are not average velocities. Okay, so please note that. Okay, so this is something that you should note, that these are not average velocities, but these are incremental velocities. Now so what we did get is x dot is equal to, let's just go back and look at that matrix again. So this x dot is equal to j into theta dot. This full thing is my j. Okay, it's a 2 by 2 matrix. So x dot is equal to j into theta dot, where j is the Jacobian. So the Jacobian relates the end effective velocity. So j relates the end effective velocity to joint velocity. Okay, so this we understand, that j relates the end effective velocity to the joint velocity. So in terms of control, so for a desired end effective velocity, you need to find the joint velocity, right? So to control, what is required? So let me draw the robot manipulator here again. Now suppose I want this manipulator to move in this point, this point, this point, like this, with this velocity. So I want an x dot and a y dot, and the controller has to actually enforce that x dot and y dot. How does it do that? By giving a voltage here. So basically it is controlling theta 1 dot and theta 2 dot. So when I give a different voltage to the motor, what happens? The motor velocity changes. So I'm controlling theta 1 dot and theta 2 dot, and as a result of which I'm controlling my x dot and y dot. So to get a desired end effector, so to get a desired end effector velocity, okay, to get a desired end effector velocity, we need to compute or find the corresponding joint velocity. Okay, so suppose I want this to move in 1 meter per second. Okay, so x dot is equal to y dot is equal to 1 meter per second. Now corresponding to that, what should be theta 1 dot and theta 2 dot, because I'm controlling the motors. So I need to know what is theta 1 dot and theta 2 dot to get this. And how do I do that? I basically have to take the inverse. So x dot is equal to j inverse of x dot. Okay, so if I give you this, you should be able to tell me what is the joint velocity. That's what the controller needs. Okay, so let's look at this equation again, and let's also look at the matrix. Please remember, this is a 2 by 2 matrix. Okay, so this one is a 2 by 2 matrix here. So theta dot is equal to j into x dot. So theta dot is equal to j inverse of x dot. Sorry, yeah. So theta dot is equal to j inverse of x dot, which is equal to, what is the inverse of j? It is adjoint of j, j divided by determinant of j into x dot. Okay, so now we see that the joint velocity is equal to adjoint of j by determinant of j into the end effector velocity. So please note that this determinant of j comes in the denominator, which means that if determinant of j were to become 0, then what is going to happen? Then this will become infinity. Okay, so as the determinant of j is going towards 0, what is happening? The joint velocity is going towards infinity. Now obviously it cannot go to infinity, so this point where the determinant of j is equal to 0 is called a singularity. Okay, singularity, because end effector cannot go to that point. Now, not only can it not go to this point, it cannot even go anywhere near that point. Why? Because as it is going towards that point, the infinity is going, joint velocity is going towards infinity. So obviously it cannot go towards infinity, right? Joint velocity cannot go to infinity. So it cannot even go anywhere near there. Now this is also an indicator of energy. Okay. Now we know the theta dot or energy is proportional to theta dot. So energy consumed is proportional to theta dot. The faster it is, the more energy you need. Okay, so if you want to minimize energy, then your determinant of j should be maximum. Okay, 0 is minimum, so if determinant of j becomes maximum, then your theta dot will become minimum, right? So and that is going to be minimum energy condition. So before we go there, let us look at singularity. Now singularity is of two kinds. So singularities are of two kinds. The first type of singularity is called the boundary singularity. So it is called a boundary singularity. Okay. The second type is called a workspace interior singularity. Workspace interior singularity. Now, as the name indicates, a boundary singularity is a singularity on the boundary of the workspace, and workspace interior singularity would be a singularity which is inside the workspace. Okay. Now, how do you find the singularities? Where is the singularity? Obviously, we know the answer. Determinant of j is equal to 0. Okay, and what is j? J is this matrix. For the two-link manipulator, j is this matrix. It's a 2 by 2 matrix, right? So this is one term, this is another term, this is one term, and that is another term. So that's my j. So now suppose I want to find a singularity for this two-link manipulator. What is the singular position? So two-link manipulator singularity, two-link 2DOF planar, where is it singular? So what we do is, let me draw the two-link manipulator here. So this is my two-link manipulator. This is theta 1, that's theta 2, L1, L2 I derived with just some time back. Okay, now what was the Jacobian? Jacobian was equal to minus L1 sine 1 minus L2 sine 1 2 and minus L2 sine 1 2, and what was the next term? It was L1 cos 1 plus L2 cos 1 2 plus L2 cos 1 2. Okay, so this was okay, so this was the Jacobian, 2 by 2 Jacobian. Now, so what is the determinant of this Jacobian? Now, how do you find the determinant? You know how to find the determinant. You can multiply this into that minus of this into that. Okay, this is a 2 by 2 matrix determinant. So it looks like there is sine terms and cos terms, but then when you multiply it out, what happens is theta 1 cancels out, and we get L1 L2 sine 2 as the determinant. Okay, so it's interesting that the determinant of this matrix containing so many terms is actually L1 L2 sine 2. Okay, so now where is the singular points? So at singularity, L1 L2 sine 2 will become equal to 0, right? Now L1 and L2 cannot be 0, okay, because they are lengths. Okay, so only sine 2 can become 0. Now it implies that theta sine 2 means is equal to, at which points it will become singular? Number one is 0 and 180. Okay, so sine 2 means theta 2 becoming 0 means sine theta 2 becoming 0. Okay, so at 0 and 180 it will become singular. So where is 0 and 180? Okay, now something to note is that this is my theta 2, right? So that fellow becomes 0 when it is fully stretched, so at that point. And the second is when it is fully folded here. It comes folded, it becomes like this, like this, like this is folded, this side it comes here. That's 180. So 0 degrees and 180 corresponds to these positions. Now something to note, interesting to note is that, so something to interesting to note is that singularity does not depend on theta 1. So something very, very important, that it does not depend on theta 1, it depends only on theta 2. So so these are 2 points for theta 2 equal to 0 and 180. There are 2 points. One point is here, okay, one point is there, another point is there. Now if I change theta 1, okay, so there can be different theta 1, so this will have a circle like that. Okay, so it is going to have a circle, okay, like that. Okay, so what we see is that it is going to have a circle here and here, so that this is going to be a circle like that. Okay, and there will be a point here. So this is my boundary singularity. Okay, so this is my boundary singularity. Now that there is no, if there is an interior singularity, it will be somewhere inside. Now 2 degree of freedom planar manipulator does not have an interior singularity. Okay, so all points inside are reachable. But some robots can have a singularity where you cannot reach inside also. Okay, so that gives us an interesting perspective on singularity and how singularity comes on the boundary of a 2 degree of freedom manipulator. We also talked about minimum energy. So minimum energy automatically implies that determinant of J should be maximum. Okay, now if you maximize determinant of J, then you'll get minimum energy. So minimum energy is maximum of determinant of J. So suppose a 2-link manipulator is performing a task. Let's say a 2-link manipulator is here. Okay, this is a 2-link manipulator performing a task. Okay, so this is my theta 1 and that's my theta 2. Okay, so this is X, that's Y. Now in this manipulator, if I take the determinant of J, we found that the determinant of J was equal to L1 L2 sine 2. Okay, sine theta 2, sine theta 1 has nothing to do with it. Okay, so what is the maximum value of this? What is max L1 L2 sine 2? Implies that it is max of sine 2. Okay, so max of sine 2 is how much? Maximum value of sine 2 is 1, which implies that theta 2 is equal to 90 degrees or 270 degrees. Okay, so what should be the configuration or orientation of the manipulator to perform a task for minimum energy? Your angle theta 2 should be 90 degrees. So your angle theta 2 should be 90 degrees. Okay, this is what it means. So if you look at in this manipulator, this angle now is 90 degrees. So which means that in the workspace, if this is my full workspace, if I draw my full workspace like that, it is 90 degrees somewhere in this region. So you should perform a task in the center of the workspace. Okay, so all robots you'll find perform tasks in the center region of the workspace, and that's the reason why, so that your energy consumption is minimized. Okay, now it's also important to look that in the case of a human being, if you think a little bit, okay, when you're writing, okay, so when you're writing, pen and paper and you're writing, this angle is 90 degrees. Okay, why is this angle 90 degrees? Because you're minimizing energy. Whenever you're performing a task, you always find that this angle, okay, this angle here, this is my theta 2, is going to be 90 degrees. So whenever you perform a task, you ensure that your theta 2 angle in the arm is 90, such that your energy consumption is minimum. Okay, so we have evolved that way, such that we always do our tasks by minimizing our energy requirement. Okay, so now The next thing that we'll have to look at is a couple of points, well, quite a lot of points. So the point that we're trying to make is that we said that x dot is equal to j into theta dot, and theta dot is equal to j inverse of x dot, and I defined j inverse as adjoint of j by determinant of j into x dot. Now this definition is valid only for a square matrix. Suppose we end up with a manipulator like this. Okay, so there are 3 links, 1 link here, 2 link here, and third one is there. So there's theta 1, theta 2, theta 3. Okay, this is L1, L2, and L3. Okay, now this is planar, so this is still xy. So you have x is equal to L1 cos theta 1 plus L2 cos theta 1 plus theta 2 plus L3 cos theta 1 plus theta 2 plus theta 3. Similarly, you have y is equal to L1 sine 1 plus L2 sine 1 2 plus L3 sine 1 2 3. Now x and y are functions of theta 1, theta 2, and theta 3 now. So your Jacobian matrix x dot y dot, the j, will be 2 into 3, which is non-square. Okay. So this is something which we'll need to look at because these are called redundant systems. We'll look at what happens to this concept of inverse when your matrix is non-square. Okay. So subsequently we'll be looking at redundant manipulators, hyperredundant manipulators. And in cases for that, we need to look a little bit into matrix inversion. What is the inverse of a non-square matrix? How do you find that? Okay. So before we go there, let's also look at the concept of the Jacobian for static forces. So this basically says that in the case of a manipulator, okay, we have the joint velocities and the end effector velocities which are related, theta 1, theta 2, and theta 3 dots. They are related by the Jacobian. What about forces? Suppose there is a static force which is acting here, F. Are the static forces acting at the end effector? So is there some relation between the end effector force and the joint torques? That's joint 3, joint 2, and this tau 1. Is there any relation between the torques at the joints and forces acting at the end effector? Because we know that in the physical world, if the velocities are related, then the forces also have to be related in terms of energy. So let's look at the other function of the Jacobian, which is called static force or transmission of static force in manipulators. So let us look at the static force in manipulators. After this, we'll come back to the matrix inversion part. We'll come back to the Jacobian and see that if you have non-square Jacobian, what do you do? And is there an indicator which actually shows you that in which direction in space should you move to minimize your energy? Okay, but before going there, let us just finish off the static force analysis for the manipulator, and then we'll come back again. So this is a generalized view of a link. Okay, it's in 3D, so it can have any shape. So I'm just drawing it this way. Okay, so this is one frame, and there is another frame, the next frame. So let us say this is my frame which is called I, and this is the frame I plus 1. Okay, now let us say that at this point we have forces and moments acting. There's the force Fi and there's a moment Ni acting there. And on the next link here, there is a force acting here. Also there is an Ni plus 1 and there is a force Fi plus 1. And there's a distance between these two joints. So this is my Fi plus 1. So there's a distance between them. The distance between this and this is, let's say, Pi plus 1. Okay. So I want to find the relation between the force from one link to the other link. So what is the meaning of this? Let me come back here and give you an example so that it's clear here. So I have a manipulator here and there is a force acting at the end effector, which is my force F. Okay, let's call this force acting at end effector. Now this force will cause forces and moments at every joint. Okay, so this force and moment will cause a force and moment here. So it's like forces move in this direction, forces and moments. So because of that end effector force or moment, it can be a moment also, or force and moment, these forces and moments will cause corresponding joint torques in subsequent joints till the base. So we want to see what is the relation between this force from this to this joint. So from this joint to the next joint, what is the corresponding way in which the forces and moments move? Okay, or the effect of, so let's in this case, effect of Ni plus 1 and Fi plus 1 on the previous joint, okay. That means if I have a force and moment at the end effector, this force and moments are going to cause torques on all subsequent joints right up to the end, to the base. So let us now, we are talking about statics, it's not dynamics. So the system is in static equilibrium. Okay, so the first thing to note here is that the system is in static equilibrium, which means that sigma f x, y, z must be equal to 0 and sigma m x, y, z must be equal to 0. That means forces and moments in the x, y, z directions must be equal. So there are 3 equations here, 3 equations there. Okay, so if I do that in general form, I can write Fi I is equal to Ri I plus 1 into Fi plus 1. What is the meaning of this? This means sigma f is equal to 0. If I use this equation, I get that Fi, the force here, is equal to the force which is Fi plus 1, which is going to act on that, and both the forces have to be equal. Okay, or Fi minus Fi plus 1 must be equal to 0, which is this equation. Okay. Now the frames are different, and hence I put a rotation matrix there. Okay, now what is this convention of Fii? It means that, so it basically means the force expressed, here, it means force acting on I plus 1 frame expressed in ith frame. Okay, so I plus 1 is being expressed in ith frame, that's why it's an I there. Okay, so this is one force equation. What about moment equation? The moment equation is going to be Ni, means in the ith frame will be equal to the moment which is coming from the other frame, I into I plus 1. Sorry. So let me just repeat what I said. So what it basically means is the ith frame acting on ith one expressed in I plus 1th frame. Okay, so this is the force which is acting on the I plus 1th frame. It is expressed in I plus 1th frame. So I'm multiplying this with the rotation matrix, and then it is getting converted to the ith frame. Okay, so I'm doing the sum actually on the ith frame. So I'm taking the forces on the I plus 1th frame and then multiplying with the rotation matrix and coming here. So in terms of the moment, it is I plus 1. So moment acting on the I plus 1th frame expressed in itself, which is the ith frame, plus pi I plus 1. Okay, so this will become force into moment. So there's going to be an R I into I plus 1 into F I plus 1 I plus 1. Okay, so you know that there is a force acting here. There's a force acting here. So the force also will cause there will be a force transmitted on this side, plus this force will cause a moment, and that is what is coming here. So that moment will be this force into the distance pi plus 1. Okay, so now if you look at this term here, that is the distance into the force. Now this much is equal to this much, right? So what I can write this term as, so I'm able to write this term as II is equal to I into I plus 1 R into I plus 1 N into I plus 1 plus Pi I plus 1 into Fii. So I'm using this equation and putting this here. Okay, so we have two equations which are used successively. So the first equation is the forces acting on frame I expressed in frame I is equal to Ri I plus 1 into I plus 1 into Fi plus 1. This means the force acting on frame I plus 1 expressed in I plus 1. It is getting multiplied with the rotation matrix and is getting expressed that side. It's getting expressed in ith frame. and moment is an I acting on ith frame expressed in ith frame is equal to the rotation matrix I plus 1. So the rotation matrix into, so this is I plus 1 into n, the moment was acting at I plus 1th frame expressed in I plus 1th frame, plus pi into I plus 1 into cross fi I. Okay, so there is a cross here, so I missed out the cross. So this is pi, so the distance is pi into I plus 1, and this is cross product. Okay, so this is p cross that. Okay, so this gives us two equations. One is a force equation, which says how the forces are moving down from the end effector towards the, and this is the moment equation, which gives us how the moment is moving from the end effector towards the base frames. Okay, so let's look at a very small example before we proceed. So let us see this very small, very simple example of a manipulator, which is like this. And okay, so these are two link manipulators. There is a tau 1 there, so that's my tau 1, and that's a tau 2 there. And let us assign axis. So if you assign axis, this is going to become my z0, z1, this is going to become z2. Okay, this is my z3. Okay. My x0 is here, x1 is this side, x2 is this side, and then x3 is that side. Okay, now let's say that there is a force and there is a force which is acting here. Let's call this force acting on, so F3 acting on frame 3 origin. Okay, now let's say this force F3 is equal to Fx, Fy, and 0. So what we need to do, what we understand is that this force is acting Fx, Fy, and 0, and this is expressed in frame 3. This is the meaning of F33. Okay, so if I say F33, it's like the frame, it's acting on frame 3 and it is expressed in frame 3. Okay, so these are two link manipulator with a force acting at the end effector at the end there. I want to find what is tau 1 and tau 2. What are the torques acting at the joints? So what we do here is we use this matrix repeatedly. So if the force F3 is acting at the joint 2, what is the force acting at joint 1? F3 is acting at 3. This is my frame 3. What is the force acting at joint 2? This is my joint 2 and this is my joint 1. Okay. So F22 will be equal to Fx, Fy, and 0, because there is no angle between the x-axis. So whatever is the force acting on joint 3 or origin of frame 3 will become same as the force acting on frame 2, right? What about the moment? So N22 will be equal to L2x2. Okay, so what is the moment acting on frame 3? So moment acting on frame 3 is 0. So moment acting on frame 3 was equal to 0. So this will be 0. What is left is this one only. Okay, so which is equal to PIA is there's a distance of L2. This is my L1, that's my L2 link length. Okay, so L2 in cross of Fx, Fy, 0, which is equal to 0, 0, L2 Fy. Okay, now you could have written that just like that also, because if there is a force acting F3, the only force that can cause a moment, so the force along the x direction cannot cause a moment, okay, because it is going along the x-axis passing, whereas this Fy fellow here, that is the one that will cause a moment, Fy into the distance L2. Okay, now that there will be a moment at the joint, and that is what we're getting here. Next is, what about F11? F11 is equal to, now there is a rotation angle there involved. So what is the rotation angle there? So there's an R angle there because there's an angle between frame 1 and frame 2. So it is cos 2 minus sine 2, sine 2 cos 2, 0, 0, 1, 0, 0 into F. So it will become equal to into the next frame, which was f2. So what was f2? fx, fy, and 0. I'm following this equation. So if this equation is equal to f1, 1, then this will become r into f22. f22 is this one. Okay. So what I get is, and this is equal to cos 2 fx minus sin 2 fy, sin 2 fx plus cos 2 fy, 0. Okay, so this is my f11, the force acting at joint 1. Now I need the moment. So what is n1? n11, I go back to the previous. So this is my n11, right? So n11 is equal to what? So here I'm going to use my moment equation. So the moment equation gives me n11 is equal to r12. Let me go back and explain it here. So this is going to give me my moment on the ith link, which is equal to, there is a rotation matrix. There is a rotation matrix here, r into the moment n2, okay, plus there is a distance pi cross force f2, okay, cross force fi. So this is force f1. Okay, so what I'm getting is, I'm getting the equation, I'm writing this equation. n1 is equal to 1 to 2, then 2n2 plus, I'm just following that, okay, p1 2 cross fi f11. What is f11? f11, I just got it here. f11 is this one, this f11. And what is the moment on the previous? It is n22 was the moment that we got. So what is the moment acting on the first link? The moment acting on the first link is equal to the moment which is coming from the second joint plus the moment, because there is a force and there is a distance. Okay, so which is equal to n11 is equal to 0 0 L2 Fy. This is the moment acting on the second joint, okay, plus L1 x1. This is the distance L1 across F cross Fii, which is equal to 0 0 L1 sin 2 fx plus L1 cos 2 Fy plus L2 Fy. Okay, now if I write it in matrix form, what we see is that tau 1 is equal to L1 sin 2 fx plus L2 plus L1 cos 2 into Fy, and tau 2 is equal to L2 Fy. Okay, now if I write it in the matrix form, tau is equal to L1 sin 2 L2 plus L1 cos 2, and this is 0, this is L2, and this is equal to fx Fy. I get from here, I get this. Now this is also Jacobian, but this is expressed in third frame. This is also Jacobian, but it is expressed in the third frame. Okay, so this gives us the relationship between the forces acting at the end effector, which is there, to the joint torques, which is here. Okay, and that is also related by means of the Jacobian matrix. Now this is also 2 by 2. Okay, it's a square matrix. So subsequently we'll have to look at non-square matrices. So this was basically to show you that the forces and moments also move. Okay, so this force will be causing a force here, and this moment will be causing a moment there now. So from the end effector is coming backwards, and what governs these two motion of the moments is there is one force equation. Okay, so this is the force equation. So just keep using the force equation, and this is the moment equation. So use the force equation and then the moment equation in order to get how the forces and moments are moving. Now, so joint velocity will start going towards infinity. Okay, so singularities are points where the joint velocity goes to infinity. So wherever the joint velocity goes to infinity, obviously you cannot go there. Okay, and also you cannot go anywhere near there. So if you want to minimize the energy requirement, we have seen that you have to maximize the Jacobian, the determinant of the Jacobian, sorry. So, and we are restricted in what we did today in the sense that we are talking only about square matrices. So in the next class, we'll move on to non-square matrices and then see that what happens if your matrix is non-square. How do you find the inverse of that? Or are there other parameters also which can determine how to minimize your energy requirement. For example, if you're moving in space, I'm here,